Hello viewers, today I'll be presenting our text-to-speech system for Dzongkha on which we worked for a year. It is a collaborative project between College of Science and Technology and the Department of Culture and Dzongkha Development. Are you excited? Come with me on this journey. To begin with, let's introduce my team. My name is Sonam Rabke, and together with my friend Mr. Kamal Acharya and Mr. Sange Tenzin, we worked under the guidance of Mr. Ishi Jamso on developing this system. My presentation outline. I will be walking through introduction, problem statement, aim or objectives, methodology, data preprocessing, model development, system integration, demo, challenges and conclusion, and then reference. Let me introduce you all to what is text-to-speech, or commonly known as TTS. So it is a technology that converts written text into spoken words. Isn't it interesting? It takes textual input and generates corresponding audio outputs. It will allow the user to hear the content instead of reading it. TTS systems have numerous applications, including accessibility tools for visually impaired individuals, language learning resources, and voice assistant in various devices and applications. With the problem statement. Dzongkha is the national language of our country, Bhutan. We have many individuals who can speak Dzongkha but face difficulties in reading the written script. Unfortunately, there is no currently available text-to-speech system designed for Dzongkha. This poses a challenge for Dzongkha learners and individuals who rely on auditory support for accessing written content. Therefore, our project aimed to address this problem by developing a TTS system for Dzongkha. As mentioned earlier, our aim was to develop the Dzongkha TTS system. In order to achieve that, we came up with 4 objectives, which includes conducting literature review, pre-processing text-to-speech Dzongkha corpus, train TTS model for Dzongkha, and then integrate the trained model on a web app. The methodology that we undertook for the completion of the project. First, we identified the problem, then we did requirement gathering. We got our dataset from the DCDD, and then we did data preprocessing. After that, we trained our TTS model, and then we integrated into a web application, and then the project was ready. So the literature review and documentation was throughout the project. The dataset preprocessing. First, the dataset acquisition. We got a total of 8,793 audio and text pairs from the DCDD, provided in an Excel file. Next, the format conversion. The audio files were in the M4A format, which we converted to WAV using FFmpeg, and then downsampling. Since the original audio was recorded at a sample rate of 48,000 kHz, we downsampled it to 22,050 kHz. This downsampling was necessary to optimize the audio for our TTS model. And the 4th, transliteration process. We transliterated the complex Dzongkha text into English letters, and then the compilation to metadata.csv. The audio was stored in the WAV folder, and their corresponding texts were recorded in the metadata.csv file. For training our TTS model, we utilized an advanced architecture that consists of an encoder, a decoder, and a vocoder. The encoder component extracts high-level linguistic features from the input text. It analyzes the phonetic and linguistic patterns present in the text, capturing important information such as intonation, stress, and duration. The decoder component takes the encoded linguistic features and generates MEL spectrograms, which are representations of the speech signals in the frequency domain. These spectrograms provide detailed information about the speech characteristics, including pitch. Finally, the vocoder component converts the MEL spectrogram into waveform samples, producing the final audio output that closely resembles natural human speech. We have conducted extensive training on various text-to-speech models, including Decathlon 2, Fast Speech, Speedy Speech, NeuralHMM, and Overflow. During our experiments, we encountered challenges with Decathlon 2, Fast Speech, and Speedy Speech, as this model were unable to accurately predict output audios. We then hypothesized that this limitation was due to the limited dataset. However, our improved version of NeuralHMM called Overflow exhibited promising results. For training our NeuralHMM model, we utilized a dataset consisting of 8,793 audio and text pairs. We trained the model with a batch size of 64, a learning rate of 0.001, and it took a total of 26,300 steps. The training process lasted for approximately 16 hours and 32 minutes. To illustrate the training progress, we monitored the alignment and average loss, which are crucial indicators of the model's performance. In TTS, alignment refers to the mapping between the input text and the corresponding audio. Ideally, for natural speech, the alignment should appear as a straight diagonal line. Now, let's listen to an audio sample generated by our NeuralHMM model using data from within our dataset. We also trained our Overflow model using the same dataset of 8,793 audio and text pairs. However, this time we used a smaller batch size of 32, a learning rate of 0.001, and the training process requires 17,250 steps. The model was trained for approximately 13 hours and 47 minutes. Comparing the alignment and average loss with the NeuralHMM model, we can observe that Overflow performs significantly better. Now let's listen to an audio sample generated by our Overflow model, which demonstrates the improvement over NeuralHMM. Now, after training our Overflow model, we conducted tests using data that was not part of the training set. These tests revealed that the model-generated audio was accompanied by noises. To address this issue, we applied Facebook's denoising tools to remove the unwanted noise. Let's compare the difference between the noisy output and the denoised output by listening to both. First, without denoising. Now, after denoising. System integration. To integrate our TTS model into a practical application, we developed a web app using the Flux framework. The front end of the web app includes a text area where user can enter Dzongkha text, as well as a generate button to initiate the TTS process. In the backend, we incorporated a widely transliteration tool to convert Dzongkha text into English letters. Then, this transliterated text is then fed into our model to predict the corresponding male spectrogram. The male spectrogram is finally passed to the vocoder, which generates the audio output. The resulting output is displayed in the user interface. Now, let's proceed to a live demonstration of our web app. For the demonstration, we have prepared a sample text extracted from Kinsel, a Dzongkha news source. It's important to note that the length of the text affects the inference time of our system. Shorter text generally result in shorter inference time, while longer text require more processing time. Let's proceed with the demonstration and observe the performance of our TTS model. After successfully integrating our TTS model into the web app, we successfully hosted it on our campus server. This web app not only features our TTS model, but also integrates with other natural language processing projects that our classmates did. We encourage all of you to try out our TTS system by visiting the provided link. Thank you for your attention, and do visit and support our project.